How's it going, everyone? Today we're going to be deriving the 4 kinematic equations in physics using only algebra, so no calculus today. To start off, we have x, which is a position in space. If you define, say, x1 as one position in space, and then some space away from that, x2, you can define a vector quantity between them, say x2 minus x1 equals delta x, where the delta stands for change, and this is a vector. Obviously, in real life, it takes some time for things to travel between two locations in space. So this quantity, delta x, takes some time to move between. And this entire quantity, delta x over delta t, is equal to the average velocity that it takes to go from those 2 points in space. Now, we can further define a quantity called define a quantity called acceleration, which is the change in velocity with respect to time. So the velocity is the change of position with respect to time. Change in position with respect to time. Acceleration is one level more, change of velocity with respect to time. And this is the average acceleration. Now, if delta A is 0, meaning that the acceleration is constant, then the following things apply. Erase this. So if delta A is equal to 0, then average velocity is equal to the change. Jesus, what am I doing? Acceleration is equal to change in velocity over change in time. If we multiply the delta t to the other side, we get delta v is equal to a delta t. Delta just means change, so a final quantity minus an initial quantity. If we expand this, we have some v final minus v initial. These are the same thing, just expanded it, is equal to the acceleration times some final time minus some initial time. Now, most of the time in a problem, you can define the initial time, ti, is equal to 0. This makes everything easier. You start the problem at t equals 0, 0 time. So we can get rid of this. And this will go to the final velocity minus the initial velocity is equal to acceleration times total amount of time that elapses in the problem. Bring the initial velocity to the other side. Y just looks nicer. V final equals V initial plus a t. This is the first of our 4 kinematic equations that can be used to solve problems with constant acceleration. So I'll call this number 1, Roman numeral number 1. For the second one, we further need to define. So again, the average velocity is equal to delta x over delta t. That's the average velocity that it takes in time to travel from this one location in space to the other location in space. But the average of anything is also defined to be the sum of whatever it is, say any number of quantities divided by the number itself. of the quantities. So if you have a list of 5 numbers, you add up the values in the list and then divide by the number of numbers in the list. So in this simple scenario, we're talking about moving from one position in space to another. There are 2 velocities, a final and an initial. So we add them up and then divide by 2, 1, 2. And this will give us also the average velocity throughout this trip. So we have 2 things equal to the same average velocity. Means we can set them equal to each other. Delta x over delta t is equal to v final plus v initial divided by 2. And then let us solve for v final. So this is, and then again, this delta t we can just replace with t because t initial is 0. So we have 2 delta x over t is equal to v final plus v initial. Let's bring the v initial to the other side. 2 delta x over t minus v initial is equal to v final. What else is equal to v final? The first kinematic equation. Let's set them equal to each other. Equal to vi plus at. Minus vi on this side, positive vi on this side. 2 delta x over t, bring this over, is equal to 2 vi plus at. Let us multiply the t on both sides and divide by 2 on both sides. Delta x is equal to vit, right, divided by 2 times t, plus at squared over 2. Let's expand this. Let's expand this delta x. It's nothing more than x final minus x initial. So x final minus x initial is equal to initial velocity times time plus acceleration times time squared over 2. Let's add the initial x on both sides. X final equal to x initial plus initial velocity times time plus 1/2 at squared. This is our second kinematic equation, Roman numeral number 2. First, second. We got the second using the first plus another bit of information, the definition of the average, and it also being equal to delta x over delta t. We use that combined with the fact that the average is defined as the sum of the velocities divided by the number, and combined with the first kinematic equation, we were able to derive the second one. I'll keep these over here. So 1 is v final equals v initial plus at, and 2 is keep those there. The way we get the third one is going to involve both of the first 2. So if you see, let's take the first one, which is vf equals vi plus at, and let's solve for t. vf minus vi over a is equal to t. That's pretty obvious. Now, the second equation has t's in it. Let us substitute this expression for t in the second kinematic equation. So into, we get x final equals x initial plus vi times, instead of t, vf minus vi over a plus 1/2 a, instead of t squared, vf minus vi over a squared. Just algebra now to simplify. Xf equals xi plus vf vi minus vi squared over a plus a over 2 times vf squared minus vi squared minus 2vf vi over a squared. I just FOILed that. One of these a's is going to cancel with this a, and we are left with x final equals x initial plus so in this term there's a 2a on the denominator, and in this term there's just an a. In order to add these terms together, we need a common denominator. So I'm going to multiply both the numerator and denominator of this term by 2. It's 2 over 2. So I'll multiply the term by 2 over 2. It's the same as multiplying by 1. It doesn't change anything, but it'll allow us to combine these as they now have the same denominator. So 2vf vi minus 2vi squared over 2a plus vf squared minus vi squared minus 2vf vi over 2a. These now have the same denominator. We can treat it as one term. Okay, minus 2vf vi plus 2vf vi. This is a plus. This is a plus. Minus vi times minus vi is vi squared, not minus vi squared. That's a plus. 2vf vi minus 2vf vi, 0. Minus 2vi squared plus 1vi squared is minus 1vi squared. Xf equals xi plus vf squared, right? Vf squared minus 1 vi squared minus vi squared over 2a. Okay, let us subtract xi from both sides. Xf minus xi equals delta x equals vf squared minus vi squared over 2a. Let us multiply by 2a on both sides. 2a delta x equals vf squared minus vi squared. And that's our third kinematic equation. Notice that this one has no time in it. So it's referred to as the time-independent kinematic equation. Sometimes in a physics word problem, you'll be offered bits of information and asked to solve for a quantity, but you're not given the amount of time. That's an indicator that you could probably use this one, as there's no time needed. So that's the third one. I'll add it up here. Number 3. Vf squared minus vi squared equals 2a delta x. There is one more equation, and we've already seen a hint. It has already been hinted at. We just need to expressly write it down. So back when we were deriving the second one, we defined the average velocity as v final plus v initial over 2. That's just the it's just the algebraic mean. And this is also equal to delta x over delta t. Remember, delta t equals t if t0 equals 0. Let's multiply both sides by t. Vf plus Vi quantity times t over 2 equals delta x. This is a true thing. And let's call it number 4. Delta x equals Vf plus Vi times t over 2. So here we have the 4 kinematic equations in physics that apply if the acceleration is constant. These can be used to solve a variety of different basic physics problems, and we just showed how they can be derived using only basic algebra and knowledge of physical quantities. In the next video, I'll show how we can derive these in a bit more of a sophisticated way using calculus, but it's not necessary. And then after that, we'll explore how we can apply these to certain physics word problems to solve kinematic problems. Thank you for watching.